Question 6 is about two instruments, and so we will study how multiple instruments are used for endogenous variable. So simple one endogenous variable, and by the way, everything is scalar and have zero mean, so it is the simplest possible example. But we have two instruments, Z1 and Z2. They satisfy exogeneity and relevance, of course. And also for additional simplicity, we are assuming homoscedasticity. Okay, so let's think about it. So part A, what is the moment functions? So the basis of our estimator is z1i ui is 0, expectation z2i ui is 0. So we are going to estimate one parameter beta for from these two moment restrictions. So you may write the function as z1i, z2i, yi minus beta xi. Okay, straightforward. And part B, if you differentiate the moment function with respect to beta, you are going to get minus z1i, z2i times xi. Okay, so so if you define g0 as the derivative evaluated at the true beta, and it does not depend on beta, it is minus expectation z1i xi, expectation z2i xi. So from now on, everywhere wherever you are going, z1 and z2 will be kind of parallel. Okay, so C is about omega. Omega is defined as gi beta 0 and gi beta 0 transpose. That is ui squared. So this much will become, if you plug in beta 0, then this will become ui. So ui will be easily factored out. And then z1i, z2i times z1i, z2i transpose. Using the homoscedasticity assumption, we are going to use sigma squared, and then it is 2 by 2 matrix z1i squared, expectation z1i, z2i multiplied, expectation z1i, z2i, expectation z2i squared. Okay, that is omega. Now then, we need to think about weight. Of course, we know the best weight is omega inverse, but I said we need to calculate this in finite sample. Especially so expectations are not that hard to calculate, but this part is a problem. So instead of using sigma omega inverse as a weight, I'm going to use omega inverse times sigma squared. So you don't need to estimate the details. We are going to get just 1 over n z1 squared, 1 over n summation z1i, z2i, 1 over n summation z1i, z2i, 1 over n summation z2i squared. This much is this part. Okay, so we are going to take its inverse. Okay, so you may do it by hand, or you may do it on computer. It's up to you. I'm not going to calculate this any further, right? Because the next question, we are going to calculate the asymptotic variance. The asymptotic variance in the end takes the form of G0 transpose W G0 inverse G0 transpose W omega W G0 G0 transpose W G0 inverse. That is our formula. It's so for in here, I I am going to calculate this first, like so. Let's see. This guy will become sigma squared times G0 transpose omega inverse G0. Okay, so don't forget this much. And the middle term becomes W times omega is sigma squared. Okay, because W is omega inverse times sigma squared. So sigma squared, omega inverse. So you are going to get actually 2 sigma squared. Sigma to the 4 times omega inverse G0. Right? Finally, same thing. Sigma squared G0 transpose omega inverse G0 inverse. Okay, as you see, there are 2 sigma squared on both sides, and there are also 2. So they will be gone. And then again, you are going to cancel whole part. So in the end, you get the same asymptotic variance as if you are using the optimal weighting matrix omega inverse, right? So as I said, constant multiplication does not matter. And also theoretically, it does not matter. It will cancel out all the time. So now then, we have to calculate this guy. That is annoying. So let me calculate omega inverse. Omega inverse is, so remember, omega looked like this. This is omega. We are going to invert this. So first I will start with 1 over sigma squared. And then I'm going to think about expectation z1i squared times expectation z2i squared minus expectation z1, z2 squared. This is determinant. And expectation z2 squared minus expectation z1, z2 minus expectation z1i, z2i, expectation z1i squared. Okay, so notation is very annoying again. We need to multiply vectors to this. So I will simplify this way. So z2 squared will be denoted as z22. And this will be denoted as z12 minus z12, z11. Then the denominator is z11, z22 minus z12 squared. That is what we are going to get. Now you have to multiply G0. G0 is, remember, expectation Z1i xi, expectation Z2i xi, right? Also, I will simplify this guy as just x1 and x2, right? x1, I will denote them as x1. x1 is x times z1, and then that's expectation, right? Expectation of z1 times x. Okay, so now we have to calculate this guy. Okay, so let's do this part first. Okay, this is x1, x2 times 1 over sigma squared times 1 over determinant. Let me just simplify its determinant. And z22 minus z12 minus z12, z11. Let's do the math. All right, so 1 over sigma squared times determinant, and then multiply x1 z22 minus x2 z12. It is 1 by 2 matrix. And then x2 z11 minus x1 z12. Now then, you additionally multiply g0 to there, right? So in that case, square times determinant times z22 minus x2 z12, x2 z11 minus x1 z12 times x1 x2. It is what you are calculating. So if you do this, sigma squared, sigma 1 over sigma squared times determinant, and it is just 1 by 1, x1 squared z22 plus x2 squared z11 minus 2 times x1 x2 z12. This is this matrix multiplication. And then the asymptotic variance is its inverse. G0 transpose omega inverse G0 inverse, right? That is sigma squared times determinant in the numerator, and I don't remember, x1 squared z22 plus x2 squared z11 minus 2 times x1 times x2 times z12. Right, just in case we are abusing a lot of notation, so let me fix that. Determinant looked like expectation of z1 times expectation of z2 squared, z2 squared minus expectation of z1i, z2i squared. That's numerator. And expectation x1 is xi times z1i squared times expectation z2i squared plus expectation xi z 2i total squared times expectation z1 squared minus 2 times expectation xz1 expectation xz2 times expectation z1 z2. Okay, so it's very annoying, a long variance. Okay, this is the variance. Now I think there is nothing you can simplify right now, so I will compare. Let's compare this with, so if you use, say, z1 only, then you can calculate the variance pretty easily. We did it in another question. Or you may just set the weighting matrix as 1 0 0 0. So that is also possible. If you use this, then your variance will be, say, let's say when you use 2, when you use 1 IV, then the variance becomes sigma squared times expectation z1i squared divided by expectation xi times z1i total squared. We have to compare now. I'd like to compare which is better. Like, I expect this should be smaller, right? That's like for like if you use two instrumental variables, then your estimator should be better. So the more complicated variance using two instrumental variables must be smaller. I'm going to prove that. So to do that, let's simplify the notation again. And first, I'm going to just drop sigma squared. They are the same thing, so they don't matter right now. So then what we want to show here is z11 z22 minus z12 squared. That is in the numerator. And remember, x1 squared z22 plus x2 squared z11 minus 2 times x1 times x2 times z12 was the variance, right? Let me double check. Okay, so I'm using the same notation, and this is right. And I will claim that I'd like to show that this is smaller than this case where z11 divided by x1 squared. That's, let me double check again. Here, this is the variance. So we would like to prove this. How can you do that? Let's first multiply here like that and move this term to here. So then x1 squared z11 z22 minus x1 squared z12 squared should be smaller than x1 squared z11 z22 plus x2 squared z11 squared minus 2x1 x2 z11 z12. That is simple, like rearranging. And by the way, it is possible because everything should be positive, right? Denominator should be positive using the, what is the, like, inequalities. So these are cancelled out. And then you will get what you need to show here is x2 squared times z11 squared minus 2 times x1, x2, z11 times z12 plus x1 squared, z12 squared should be positive, right? This is equivalent. And this is clear because it is x2z11 minus x1z12 total square, which is always positive. So it is, and let's put it like weak inequality. This is greater than or equal to 0. And they are equal only if x2z11 equals x1z12, right? That is expectation of xi z2i times expectation z1i squared equals expectation xi z1i times expectation z1 z2. We have seen this in on earlier problem set, right? In chapter 2. So this is an identification problem. So like otherwise, if this equality is not true, then always you will get a smaller variance whenever you use two instruments with the optimal weighting scheme. Okay.